Talk about classifying matter into two major groups, mixtures and pure substances. That's on page 69. In the blue, the definition of each is given. We covered it yesterday. So a substance that contains only one element or compound is a pure substance. If we go back to our Duplo model here, if I were to have, and I think you all figured out now that these are like supposed to be atoms or whatever of the same element if they're the same color. So if I look into my sample that I have in my hand, and I look inside of that, and what I find is that I have all of the same stuff. I look through my hand, I've got all the same stuff. And in this case, if it's all the same stuff and it's all the same atoms, right, then I know that I have an element. Atoms of an element. And what I have is a pure substance because all I have are atoms of the same element. It's a pure substance. Everything in my hand is exactly the same. In this case, they're all going to be atoms. If there were to be some kind of structure that I had in my hand, I can only make one of them now because of my limited grip or whatever, but let's put these together. And let's say that in my hand, I had a structure that I had not just one of these structures, but I had a handful, and every one of the things in my hand looked exactly like this. I had multiple copies of the same exact thing. Well, using our analogy, this would be a compound. It would be known as a molecule of a compound. And since everything in my hand looks exactly the same as the structure, I could still say I have a pure substance. Because everything in my hand is a copy of this. They're the same things. Okay? So the fact that you've got a pure substance doesn't mean that every atom in your hand is the same atom. It would be in the case of an element, but it could also be everything in my hand is the same structure, the same molecule. And since everything is exactly the same structure, it's a pure substance. A mixture is when different elements or compounds are in your hand. For example, if in this case I have two yellows and a red, I have a mixture now. Because in this case, the atoms that are in my hand are not all the same. I've got two atoms of one element and one atom of another element. And so when I hold them together, it's not a pure substance because every structure in my hand is not identical. If, however, we were to make a compound out of them, like H2O, if everything in my hand was exactly the same as this, I would have a pure substance again. Okay? So a mixture means in your hand, things are different. Pure substance means everything in your sample is exactly the same, whether it's an atom of an element or a molecule of a compound. It's the same thing. Pure substances contains only one particular element or one particular compound, whereas a mixture contains different compounds or elements all mixed in together. And we used the example from the book. We saw the picture of the iron and sulfur mixture. So if I have a sample that's 100% iron, it's a pure substance. And if I have a sample that's 100% sugar, and sugar is a molecule, but if everything in my hand is sugar, I still have a pure substance. But if I have iron and sugar atoms mixed together, remember the picture of the black iron and we have the white, to us looks like white sugar. We mix those together. They don't combine chemically automatically and form a new molecule. They stay separate. We would then have a mixture in our hands. And if we take something and we dissolve it in a liquid, in the case we have sugar, we put the sugar in H2O, water, and we stir it up. What do we have? Do we have a third kind of molecule? Has the sugar and the water, have they broken their bonds with each other and then come together and formed a new substance? What's happened when we dissolve sugar in water? Has a chemical reaction taken place? No, it hasn't. In this case, what's happened is the sugar molecules are in the water, but they now become surrounded and they get separated from each other by the water. The reason why we can see sugar in our hand is not because we see each individual molecule with sugar, but because we see gobs and gobs and gobs, it's a scientific term, gobs and gobs and gobs of sugar all stuck together, so it's big enough that we can actually see it. But when we put it in a liquid, in the case of water, and we stir it up, and it seems to disappear. The reason it disappears is because each molecule of sugar is now completely surrounded by water. It's broken away from its neighbor, and that little piece is too small for you to see. And so it appears to disappear. It appears to react, but it doesn't actually react. And if we were to go and heat the water to the point where it starts to boil off and evaporate, when all the water's evaporated off, we would have sugar left at the bottom. So sugar, salt, whatever, mixed into a liquid doesn't react. It necessarily react. It could, but it doesn't necessarily react to form a third thing. It may simply be the two things, but now they're thoroughly mixed together. And when sugar is mixed in water and you have a sugar-water mixture, the sugar molecules are so far apart from each other that we can't see them any longer. We mentioned yesterday that mixtures can be physically separated based upon each substance's properties. Yesterday we used the example of iron and sulfur being together and using a magnet, because iron is magnetic and sulfur is not. And so by passing a magnet between this mixture, certain things will have a response and certain things will not. So if we can find the distinctive attributes of each one of the components, we can do something in the lab. We can go through a physical process to separate them. So mixtures can be physically separated. Pure substances need some kind of chemical reaction to separate them. Okay? So molecule sugar, you don't just simply take the pieces apart. You've got to put energy into it. You've got to create a reaction that's going to cause all the atoms that come together to form sugar to break apart to get something else. Same example we talked through yesterday, so I'm not going to spend a lot of time on it. We talked through it in detail. Mixture, iron's magnetic, sulfur's not. Pass the magnet, you pull out the metal, the iron, you leave the sulfur behind. And so you physically separated them that way. We mentioned that below that in your book, again, we are reviewing back through page 70 now, but at the bottom of your book you see the iron sulfide. This is the same iron and the same sulfur from the first set of diagrams. However, they have been reacted to each other and have made a third thing, a new compound. That compound is not magnetic, and so passing the magnet through it, nothing happens. And we can't separate this sulfur and iron any longer simply by physical means. We've got to use a chemical process to break those two atoms apart, so it's no longer a molecule of iron sulfide, but individual atoms of iron and sulfur, to use the same method again. So, classifying mixtures. This, I believe, is the last section of the module. We started this yesterday talking about homogeneous and heterogeneous mixtures. Again, on page 73, you can see the definitions in blue, meaning you need to know them for the exam. Just like every other term in blue, it's important that you know those, have those memorized. So a homogeneous mixture, a mixture with a composition that is always the same no matter what part of the sample is observed. Again, I go back to the simple analogy of having a handful of something. That's your sample. If I have a handful of something, whatever it is, and if no matter where I go inside my sample to draw a piece out of, no matter where I go in and take like a biopsy and cut something out, right? No matter where I go in this, whenever I look at one part and I go and look at another part, it's going to be exactly the same. If something is homogeneous, it means it's the same throughout. There's no differences between one part of the sample and another part of the sample. We'll get some practical examples in a minute to help us out here. The heterogeneous mixture. It's a mixture with a composition that is different depending on what part of the sample you're looking at. As I have the sample in my hand, I look at it and I go, hey, there's distinct parts. This part over here is very different from this part over here in my hand. Or maybe if I'm looking at it in a glass instrument, like a graduated cylinder. Hey, the bottom is different than the middle, which is different than the top. It's got different parts in it. If it separates out, if there's parts that are different from other parts, it's then heterogeneous. It's not the same. Homo meaning same, hetero meaning different. So it's different in places. Homo same, hetero different. So some examples of homogeneous mixtures. Salt water. If I take salt, mix it in water, I just mentioned with sugar how dissolving just really means taking the individual molecules of whatever you have and water completely getting around it. Now, sugar is covalent, so it's not going to dissolve and break apart in water, but sodium chloride, salt, it's ionic, right? Sodium is a metal, it's ionic. What happens to ionics when you dissolve those is the sodiums and the chlorines actually do break apart. Water gets in between the sodiums and the chlorines, and so you've got ions now in the water. But when you mix it up, as we look at it, there's no part of my mixture where one part is not salty. You know what I'm saying? If you're thoroughly mixing this thing, every piece is the same. So you wouldn't say, hey, I'm going to take a straw and drink from this. I'm going to take the straw and put it at the bottom, because at the bottom is where the fresh water is at, and at the top is where the salt water is at. It's thoroughly, if you thoroughly mix it, it's the same throughout, everywhere. Also, Coke. You drink a Coke. Now I know there are some extremes, but you pop this thing open, you're not saying, hey, you take the first drink, because that's the best part of the Coke, right? I'll drink the bottom of the can, because it's not the same at the bottom. It's generally the same. It's the same throughout the entire sample. So there is no part that's better or worse because things separate out. Now you can have drinks that separate out, right? There's certain drinks that before you open up the bottle or the can, you shake it up first. Or you may take a drink out of it and then recap it so there's some shake space, and then you shake it up again to try to make it homogeneous. But in these cases, it's going to be the same throughout. And so it's a homogeneous mixture. Steel. Steel is not, there is no element known as steel. Steel is a combination of iron and other elements, specifically carbon. And so to make steel, and to have steel that's the appropriate strength, you can't have areas that are different from other areas. You can't, a good production is not going to have parts of the steel, parts of a beam, let's say, that are very strong and parts that are very brittle, because the mixture is different. They work very hard to make sure it's a nice, consistent mixture, so that the whole sample has a certain strength to it. And you're not, as an engineer, wondering, hey, will this actually hold people? I don't know. It depends upon how well it was mixed. You're going to mix it and make it a homogeneous mixture. It's going to be the same throughout the entire thing. Heterogeneous mixtures are a little bit more obvious. For example, Italian salad dressing. I use that because that's the example I think of. Is this homogeneous or heterogeneous? If it's heterogeneous, it's like Italian salad dressing that separates out, where you have different things that kind of, if you let it sit, you'll see different bands of things that form in the bottle. They separate out like that. So, in the case of a straw drinking Italian salad dressing, which my sister used to do when we were kids, didn't really get that. But if you were to take a straw and put it in the Italian salad dressing, you would say, hey, let me get the straw down to, let's say, to the seasonings, because I like the seasonings. I don't like the oil, or I don't like the vinegar, I don't like the whatever. You can actually probe and get to a certain level and draw off whatever you like. Because in that container, it has different levels. Every sample in there is not exactly the same. I can go to different parts of the sample to get what I want, and it's not going to be the same as in another part. That tells me that it's a heterogeneous mixture. It's not thoroughly mixed. It's not all the same everywhere. A bowl of cereal. It is not homogeneous. It's heterogeneous. Because typically the cereal either floats or sinks, right? You put the water in it. Now, unless your charms are floating, that's different. But you put your milk in it, right? And then either the cereal's going to be at the bottom with milk on top, and you dig the cereal out from the bottom, or the cereal floats on the top. If you eat O's and things like that, it's going to float to the top, and the milk's going to be underneath it. It's not going to be an even mixture of cereal and milk throughout the whole thing, so that no matter where I go, I can sample the same thing. And a cake with icing on it. How many people are in here? If you had to choose between icing and cake, who are the cake people? Okay, and who are the icing people? Okay, more hands. I agree. Cake is a transport mechanism for the icing, right? We're eating icing, we're using cake as a reason to get icing. So, and also this foolish thing about it's too rich. What is that? Too rich, I don't understand it. But if you take a piece of cake, or take a cake and you cut it down the middle and you separate the two halves and you look at it, it's very distinct that there are certain sections that have certain things. It may be a whole cake. It may be a two-layer cake and have a band of icing through the middle. It may have icing over the top. You may have fruit filling. You might have other things inside of it. I don't think we do fruit cakes anymore for Christmas. That's a distinct heterogeneous mixture. But you can see, hey, I want more icing. So where are you going to go to get more icing? You're going to wait in line to make sure you get what? An edge piece, right? Or if you're really lucky, what are you going to get? Come on, you icing people, you know what I'm talking about here. Be vulnerable. Corner piece, thank you, Lo. Wait for corner piece. Why? Because then you got a top and two sides with icing on it, right? And if you're really smart, you hang around because the people cutting will go, here, let me help, you know. You just put that big glob of lard and sugar on your plate for you to eat, right? Because you know that's what icing is, right? Okay. Anyway. So, as you're looking at this piece of cake that's iced, from the side, you can tell very clearly there are different places. If you're a cake person, you're cutting in, avoiding icing. If you're an icing person, you're eating around and saving the outer edge because you got that corner piece for last. So you get mostly icing and a little bit of cake to finish with, because it's distinctly a heterogeneous mixture. So this chart is in your book. You don't need to be able to reproduce it, but you need to be able to think through it with me. Okay. So this is how we classify everything that has matter and takes up volume. Everything, all matter, fits into this classification scheme. Everything is either a pure substance or part of a mixture. If it's an element, it either exists in a sample that is all similar to itself, it's all the same stuff, or it's in a mixture that's other elements, other atoms are in there as well. And same thing with compounds. Either you have a sample that's purely one compound, or you have a sample that is a combination of compounds, or maybe a combination of compounds and elements. It's either going to be pure, or you might think of it as impure. A pure substance or an impure substance, which we would call a mixture. From within the pure substances, it's only one compound or one element, and they can be broken down into, then, elements or compounds. If you have a pure substance and you can't break it down anymore, it's an element. But if you have a pure substance that's a compound can be decomposed down into elements. So you have pure substances which either form elements or compounds, and compounds can be broken down into elements. That's not shown on the chart here. Every one of these compounds could be broken down into their constituent elements. What are the things that come together to form the molecule, which is that substance or thing? On the other side, we have mixtures, meaning we don't have something that's pure. We have a mixture of elements, or a mixture of compound or molecules that are compounds, or we have a mixture of compounds and elements, of atoms and molecules. We've got a mix. That mix is going to be either homogeneous or heterogeneous. It's either going to be the same the whole way through, or it's going to be different in different places. Comments on mixtures. What is milk? Let's classify it. Is milk a compound? Let's start. Is it a pure substance, or is milk a mixture? I have one pure.
Mixture.
I have one of each. Okay. Very decisive group here.
Pure.
Pure. Okay, so two pure, one mixture. Anybody else with a conviction that they know what it is, pure or mixture? Have you ever? Has anybody here ever worked dairy? Ever seen raw milk before it's gone to processing?
I've seen. I've seen.
So over time, before it goes to processing, you know the big milk tanks? Sorry, I used to work dairy when I was a kid, my summer jobs. But if you take milk, raw milk, and you set it out in a jar, very quickly you're going to see the layers. You're going to see that it starts to separate out, just like Italian salad dressing. Milk is a mixture. And in fact, unprocessed, milk is a heterogeneous mixture. It will fall out into layers. Which is why, at the dairy farm, before they send it, put it in the truck to take it to the processing plant, they've got these big mixers in there, continually stirring the milk. They're trying to keep it from separating out. Keep it as homogeneous as possible. It's not until it goes to the processing plant when the milk is homogenized. Heard that phrase before? Drink homogenized milk. It's homogenized. There's a process that it goes through at the processing plant where they put it through a process that allows the milk to remain mixed in the container as it goes to the store and as you bring it home. Otherwise, like the practices on dairy farms, is before you use the raw milk that you got straight from your cows, you shake it up. Because what's going to happen is it's going to separate out. And there's going to be a band that's cream, and you can pull that cream off and you can make ice cream or butter with it. And there's a band in the middle which is a lot more, there'd be like 2% milk, right? And you take off you pull that stuff off. And then you're left with the skim milk, because it's all the fat has been skimmed off of it. And that's how you get the different grades of milk. Skim milk, 1%, 2%, whole milk is how much processing do they do to pull that milk fat off? Because the more milk fat they pull off, whatever's left, they homogenize that. They blend that together. And you drink that either as whole, they pull some off, 1%, pull more off, 2%, pull most of it off, skimmed. That's where the phrase skim milk comes from. They skim off the fat and they mix up the rest. So it's originally heterogeneous, but it's made homogeneous in process. Air is a mixture. Well, air is a mixture. Okay? In the room here, there's not a pocket over there where there's oxygen. And we don't see the different gases, but we're not all in here saying, okay, we're in chemistry class, but we have to stand up because the oxygen might all be over there. Quick, let's all go to that corner so we can breathe. Right? Go over there and breathe in that corner for a while. Well, great, guys, we depleted all the oxygen over here. We can see the carbon dioxide levels building. Oh, the strongest pocket of oxygen is now at the door. We'll run over to the door. I gotta be where the oxygen is at. It's not the way it works. Air is a mixture, and actually, like we said before, it's continually mixing, not perfectly, but continually mixing even within this space. We are sucking in a whole bunch of oxygen, and we are putting off a whole lot of carbon dioxide in this room. But the carbon dioxide that you exhale doesn't just kind of sit around your face like a bubble and slowly have you hyperventilate because you're running out of oxygen. Carbon dioxide that you exhale gets mixed up into the air, and guess what? Your neighbor gets to breathe it in a few minutes. What just came out of your mouth goes into their mouth. And so we're sharing our expelled gases in here all the time. That's part of the reason why we infect one another and stuff goes through, not only from physical contact, but through the air as well. But one of the things that's interesting, and I don't recall which of these I have on slide because I haven't used these slides in a couple years. But let me look forward, because I hate to describe something and then have it show up right on the screen. That air itself, you can see from the diagram, that air is gaseous when we exclude humidity. What is humidity? Just what does it mean if something is humid? If it's humid in here, what does that mean?
It's no air.
Well, humidity has to do with the amount of water vapor in the air. The more water is in the air, the more humid it is. The stickier feeling it is. That's from all the water in the air. The water, if we exclude that water in the air, because that water in the air may be in gaseous form, and it's beyond the scope of this class, but there is actually the sense of there's water within those things which are typically gaseous at these temperatures and pressures that we live at. But 78% of the air that we breathe is nitrogen, 21% is oxygen, and 1% are other gases. What's really interesting is that of these things, the oxygen is what we need, right? If we have too little oxygen, we start to get lightheaded, hypoxic, we start to get dizzy, we start to get altitude sicknesses due to hypoxia. Eventually, if there's not enough oxygen, we fall asleep. We look like first period chemistry students. We fall asleep where we're at. And if we don't get oxygen, we will just pass in our sleep. Just like that. Just pass in our sleep. Don't worry, 10 seconds ago I could have pointed up though. We'll just pass in our sleep because it's so restful. Because Mr. Baker isn't like Mr. Patty. He's not going to just start yelling terms. We're falling asleep. It's nice, oxygen. That's when you don't have enough oxygen. What happens when you have too much oxygen? start to hyperventilate. Every athletes, you know, when you start to hyperventilate, you take that paper bag and stick it over your mouth. Say, breathe, breathe. Oh, wait a minute. The reason you've got too much oxygen. Why am I breathing into a bag? So that you're not bringing any fresh oxygen in your system. You're exhaling carbon dioxide, and then guess what? You're breathing that same carbon dioxide right back in. And you are doing a closed system breathing so that the percent of oxygen in the bag gets lower and lower and lower as your body converts it into carbon dioxide because your system has too much oxygen. We have a band that we live in where if we've got too little oxygen, we die. We got too much oxygen, we'll die. Guess what? That band of livable space for us in terms of oxygen is maintained by 1% other gases and 78% nitrogen. Now, one of the neat things about nitrogen is, with regard to your body, it's inert. It doesn't do anything. Nitrogen is like a filler in terms of our body. Now, there are some issues that you can have with nitrogen. Most common known is like when you get the bends from scuba divers. If you go too deep and then you suddenly surface, that rapid change from high pressure to low pressure, what happens is as the pressure in your system, in your body gets greater and greater and greater by going deeper and deeper and deeper, your body will actually absorb more and more nitrogen will stay in your blood. And if you surface too quickly, the nitrogen in your blood starts to come out in the form of bubbles, and you have bubbles in your blood system. It's not cool for your brain, it's not cool for your heart, and you get the bends, and you can die from it, depending upon the rate at which you come up. How quickly this nitrogen gets released into your bloodstream in the form of bubbles. Bubbles in the blood is bad. But under most circumstances, like right now, we're breathing in nitrogen. Matter of fact, most of what we're breathing in is nitrogen. Most of what we're breathing in is nitrogen and oxygen, which make up 99% of everything. We're breathing it in. And when we exhale it, we're exhaling carbon dioxide, some oxygen that our body didn't need. We breathe in more than we need. And we're exhaling all that nitrogen we breathed in because our system doesn't need it, doesn't look at it, doesn't consider it. We breathe it in, we breathe it out. We breathe it in, we breathe it out. But it's there because it keeps our oxygen levels at the right percentage. Without the nitrogen, we would all have too much oxygen. But because of the nitrogen, which is inert, it keeps the oxygen levels that we breathe in the range that we need to live. So, kind of cool there, I think, anyway. Let's look over on page 212 on your own. Classify the following as elements, compounds, heterogeneous mixtures, or homogeneous mixtures. Mercury. Which is mercury? Is mercury an element, a compound, or a mixture? Well, if you flip over to page 77, and let's see if we can find mercury. Mercury, third column, fourth one down. Atomic symbol, Hg. Hg is a symbol for mercury. So, what is mercury? If I have a sample of mercury, I have a sample of atoms from an element. Because it's an element, is it a mixture? Or is it a pure compound? Or is it a pure substance? If I have a sample of the element mercury, they're all atoms of mercury. Is it a mixture? No. It's not a mixture. It has to be a pure substance. Because every atom in my hand would be an atom of mercury. Even if it weren't mercury, if it was a compound that had mercury in it, if everything in my hand was that compound, it would be a pure substance. It's an element. Carbon monoxide. Monocarbon monoxide, we drop the mono for the monocarbon, it's just carbon monoxide. Carbon monoxide. Is this an element, a compound, or a mixture?
Mixture.
Is it a mixture? Choices again. Is it an element? Is it an element? Is there a symbol over there for carbon monoxide? Where's the carbon monoxide block on my periodic table? No, there's not one. Why? Because we know already it's made up of two elements, carbon and oxygen. We can see that. Matter of fact, I know that it's one carbon and one oxygen because it's monocarbon monoxide. One of each. Come together to form a molecule. So I have a compound in the form of a molecule. Does that account for everything that I have? Yes. Is it? It's a compound. So because it's a compound, if that's all I have in my hand, everything is a molecule of this compound, is it a pure substance or is it a mixture? It's pure substance. It's a pure substance. Everything I have is a chocolate. Is chocolate an element? I know some of you wished you could look at the periodic table and find a symbol for chocolate, but chocolate is not an element. Now the question, is chocolate a compound? Is there a chemical formula for chocolate? No, there's not. It's not an element, it's not a compound. So it's not a pure substance. It must be then a mixture. Well, the question becomes, is it a homogeneous mixture or is it a heterogeneous mixture? Stop for a second and ask yourself, have you ever in your selfishness reserved a part of a piece of pure milk chocolate for yourself and given your friend another piece of it because you knew your side of the candy bar tasted better than his side of the candy bar? No. Because, again, this is part of production, but everywhere on the piece of milk chocolate should taste exactly like every other piece. Why? Because it is a homogeneous mixture. It's the same throughout. All the pieces that make it up are mixed throughout. And you will know if you get a bad piece of chocolate that wasn't mixed well. Have you ever had that, open up the bar and said, hey, how come one side of this thing is all weird and powdery and it's not quite right and the other side is what I expected? Some of that may be due to production. They failed to have a pure homogeneous mixture, and what you've got was more solids than liquid. That has happened. It can happen. But typically when you open up a candy bar and part of it looks all powdery, it's because you left it in the car, it heated, and then maybe you cooled it, and the heating and cooling changes the textures and the look of the chocolate. But in terms of pure milk chocolate, or in this case just chocolate, it is a mixture. It's not an element. It's not a compound. It is a mixture, and it is the same throughout, so it's a homogeneous mixture. An apple. Is there a chemical symbol for apple? No. Is there a compound that we call, this is the apple compound? No. So it is a mixture of some kind. So then, okay, once you come to the decision that it is a mixture, now the question is it the same throughout or does it have different parts? Okay, so since it has different parts, it is what kind of a mixture? A heterogeneous mixture. Because some people really like the skin, some people don't. Some people really like the flesh, some people don't. Some people actually eat the core. Some people eat the seeds. And I know somebody eats the stems. But, as crazy as that sounds, you have preferences and you know, hey, certain things are, some kids like to have it peeled, maybe because it gets in the teeth, but they peel the skin, right? And then they'll eat it, but they'll throw away the core. That whole understanding that there are pieces and parts, there's parts of the apple you like more than other parts. Don't mean to throw William under the bus, but I'm going to do it. William, what's your story about a heterogeneous mixture that you didn't understand how to consume it? Peanuts. William loves peanut butter, but he had never experienced peanuts in the shell until he went to a hockey game. And he couldn't understand why everybody loved peanuts because he was there eating peanuts with the shell on them. Okay? So how many people in here have eaten peanut shells before? Okay. Some people won't even think of it, right? It's bad enough when you crack it, maybe can't get it, so you use your teeth and you get the powder in your mouth. And I'm looking up like, why don't you like peanuts? He's like, I can't understand why people like peanuts. These are nasty. Okay? Because it's a heterogeneous mixture. You've got the nut on the inside, which is awesome, the shell on the outside, which lived underground, protecting the nut, right? As it grew. So it's a heterogeneous mixture. Different parts have different characteristics. You can't sample it in any place and get the same exact components of your sample. It's a heterogeneous mixture. Tea with no ice in it. You may. Tea with no ice. Say no ice because if ice were in it, there'd be ice on the top and no ice on the bottom, right? You'd have a difference there. But tea with no ice in it, is that an element or a compound? No, it's not an element or a compound, so it's not a pure substance. It must be a mixture. So if it's a mixture, it's either a homogeneous mixture or a heterogeneous mixture. If it, again, part of this is, can it be mixed? And if it can be mixed, if it is mixed, we're going to say it's homogeneous. It's the same everywhere. There's a pitcher of iced tea that's been, again, part of the process of making is to mix it up. But substantially, is it going to be the same from the top to the bottom if you're like at a table pouring it out here for people? Is every glass going to be basically the same? It is. We're going to call this a homogeneous mixture. Now, granted, if you let it sit and you have pieces of tea in there that aren't fully dissolved, like some pieces in it, you will tend to get that stuff residue on the bottom. Okay? We're just trying to use these as examples to get the general idea. The general idea is that throughout it's the same. That portion that's been mixed and then served. Left to extreme of settling, yeah, you're going to get some particulates that come out. Cesium. It's an element. Because it's an element, then if I have a sample of cesium, what do I have? Pure substance. Correct. So it's an element that's a pure substance. In ocean water. Ocean water is a mixture. There's no element of ocean water, and there's no compound known as ocean water. The question then becomes, is it homogeneous or is it heterogeneous? Ocean water is actually a heterogeneous mixture. The water separates out in different bands based on its salinity. So we consider ocean water to be heterogeneous. It's not the same everywhere. Barium chloride. It's not an element, but it is a compound. And therefore, if I have a sample that is all barium chloride, I have a pure substance, which is a compound. The chocolate chip cookie. The element of chocolate chip cookie doesn't exist. Compound known as chocolate chip cookie doesn't exist. It's a mixture. Because it's a mixture, you ask yourself, is it the same everywhere? Have you ever preferred one chocolate chip cookie over another chocolate chip cookie? Again, in your most benevolent times, and maybe given your friend the chocolate chip cookie which had more chocolate chips in it than yours. And the fact that there can be more chocolate chips between one cookie and another, or the fact that you could have a chocolate chip cookie and you could break off a piece that has a chocolate chip in it, or break off a piece that doesn't have a chocolate chip in it, should tell you that it's a heterogeneous mixture. Different parts have different things and look in different ways. That brings us to the end of Module 2.